In this video, we're going to show another way to start multi-GPU programming, and we call it MPI-based multi-GPU programming. It is actually very similar to thread-based multi-GPU programming, but MPI helped us start the threads, so we don't really need to do the thread programming. So as we can see, there are some APIs that is provided by MPI. For example, we have MPI init, MPI com rank, MPI com size, MPI finalize, and there are some communication primitives like scatter, gather, and also there are some MPI synchronization primitives like MPI barrier. We're going to introduce these APIs in the following example. And in this example, we're going to do a square sum, which is slightly more complex than vector add. We want to square array values, then we want to calculate the sum. So as a main program, this time we have to parse in the argc and argv, because the MPI init wants this argument to initialize the MPI environment. The next, we use this MPI com rank and MPI com size to determine the identity of each thread. This part is very similar to GPU kernels. In the kernels, we need to know the global thread ID, and sometimes we need to know the kernel size. So here it's similar. The rank is similar to thread ID, and the size is similar to grid size. And we will know from these 3 lines of code about which thread we're currently executing and how many threads are there in total. And here we're using a C method to create those random numbers in an array. Here we're using an if statement. We only perform this operation with the leading thread when the word rank equals to 0. And this word rank and the leading thread will generate many random numbers to fill the buffer. And then in each thread we create a buffer that holds a subset of the entire array. We use this scatter method to distribute these random numbers from the root thread to all the processes or all the threads in the MPI world. We're copying the first part of this buffer to the first rank, or copy the second part of this buffer to the second rank, and so on. Next, we see this part of code that we should already be very familiar with. We set a device. This is a heap runtime call. We set a device we want to use, and the device equals the rank ID. So rank 0 will use device 0, rank 1 will use device 1. It's a perfect matching because we know how many GPUs are there in the platform, and we can control how many threads we want to start. Then we perform malloc, we launch the kernel, we calculate the block size and grid size, we launch the kernel, we synchronize the kernel, and we copy the data back from the GPU to the CPU side. This part of code is very similar to a single GPU code. So at this point, we need to perform a synchronization. Previously, we have been using heap stream synchronize or have been using join method to synchronize multiple threads. And MPI provides a very convenient synchronization primitive that is called MPI barrier. Barrier means that all the threads need to arrive at this point before continue to executing. So this is an explicit synchronization that we need to guarantee all the threads arrive at this point and complete the kernel execution and copy the data back from the GPU side to the CPU side. Finally, we use this MPI gather method to gather all the data that's distributed in all the ranks to the leading rank. Note that this MPI gather and MPI scatter only works for CPU data, and there's no way for MPI to directly control GPU data. Later on, as we introduce RCCL library, we can directly apply these MPI-style communication primitives to GPU data. But here, we're only gathering CPU data. And finally, after gathering all the data to the leading rank, we calculate the leading sum. And basically, we only want one GPU to perform this sum operation. Finally, we calculate the sum. We only need one GPU to calculate the sum. We use this leading rank to implement this logic. And this part of code is similar to a single GPU code. And we're even hiding this reduction sum example. We'll talk about how to do reduction sum later. And at the end, we call this MPI finalize. As you can see from this example, the advantage of MPI is that it saves us the process of creating threads, sending data back and forth across devices. And another advantage is that sometimes we may have GPUs that is equipped on more than one machine. MPI can easily support distributed programming, but it's very hard for stream or thread-based applications to support these type of features. And we can see MPI barrier is very easy to use. It's simpler than heap stream synchronization. It's also simpler than thread dot join. And we also have this very easy to use gather and scatter method that can save us a lot of time. So let's say how to write this heap, how to compile and how to execute these MPI heap programs. When we program a regular MPI program, we typically use this MPI-CC compiler. MPI-CC is nothing special, it's just a wrapper of the regular GCC compiler. We can use this MPI-CC-show me command to show the actual command that we're going to use. For example, in my environment, this MPI-CC is actually executing this particular program. Here, this MPI-CC is actually using the GCC compiler, so we can simply replace the GCC in this command to heap-CC. And we can simply copy-paste the whole command. And finally, when we run this program, we cannot directly use /run. We have to run with this MPI run bootstrapping application. Here we use 4 threads, so we use MPI run -n = 4./main to start 4 thread and run this squared sum operation on 4 GPUs. As a summary, MPI-based multi-GPU programming is a very convenient way to control a lot of GPUs. It's very widely used in HPC applications. The method is that we want to implement the thread function as if it's a thread GPU program. At least the core part of this function is similar to a single GPU program. The MPI is responsible for starting the thread. We only need to call a few extra APIs. We need to write a special program for the leading rank. And finally, we can use these MPI communication and synchronization primitives such as barrier or gather method, which makes the communication and synchronization much easier. So far we have done 3 different methods: stream method, stream-based method, thread-based method, and MPI-based method. There's no clear good or bad method. Typically, for smaller scale applications, stream-based multi-GPU programming is good enough. If we want more independence, we can use thread-based method. And finally, if we're programming distributed large-scale multi-GPU applications, MPI-based method may be the simplest one.